Picture a modern, glowing cloud data center. Look closely at the server racks, pulsing with light, processing thousands of requests every single second. It's the beating heart of our digital world. But beneath all that immense power and speed, well, there's a hidden vulnerability. Welcome to this explainer, where we're going to unpack one of the most notoriously elusive phenomena in software engineering.
Let's set the scene with a highly simplified bank database. Imagine there's exactly $100 left in an account. Now picture two glowing API requests racing toward the server through the network, both attempting to grab that exact same $100 resource at the exact same time. They hit the server simultaneously. So what actually happens next?
First, thread A reads the balance, sees that $100 is available, and decides, great, there are sufficient funds, I'll subtract 100. But right alongside it, thread B is executing the exact same logic in perfect, dangerous parallel. Since neither operation finished before the other started, thread B also reads the balance as $100. They're both operating on a shared state, but acting as if they are completely alone. If we map this out on a timeline, at exactly the 1 millisecond mark, both threads read the same stale $100 balance. Then, at 2 milliseconds, they both subtract $100 and write a new balance of 0 back to the database. Thread A took $100, thread B took $100, but the account only dropped from $100 to 0. The final database total is completely corrupted, and the bank just lost money. Because both operations read stale data before either completed, the application entered a highly dangerous state.
Section 1. Anatomy of a data race. Let's look at the flaw itself.
What we just witnessed with that bank account is called a race condition. It's essentially a system flaw where the substantive behavior of your software becomes totally dependent on the uncontrollable sequence or timing of events. If that timing is even slightly off, you get unexpected, inconsistent, and often disastrous results. Interestingly, this timing dependency isn't some modern cloud-era problem. It's actually been crashing systems since at least 1954, when David A. Huffman first wrote about it regarding logic circuits. So it's deeply rooted in the architecture of computing itself.
And this perfectly illustrates a concept engineers affectionately and frustratingly call the Heisenbug. Because race conditions rely on highly specific, non-deterministic timing between interfering threads, they are a complete nightmare to reproduce. The very act of trying to study the bug, by adding logging or attaching a debugger, actually changes the thread timing. So the moment you look for the Heisenbug, it seems to magically vanish, only to strike again the second your system goes back into production.
Section 2. The database dilemma, and how we actually manage concurrency.
So, how do we handle these overlapping requests in the real world? Well, in a real database, operations frequently span multiple tables, queries, and updates. A database has to group these multiple read and write queries into a single logical unit of work, which we call a transaction. For example, transferring money between account A and account B requires reading A, deducting the amount, writing to A, and then repeating the inverse process for B. The database doesn't magically know this is one unified action. As developers, we have to explicitly define those boundaries.
To protect these transactions, databases rely on the ACID properties. Atomicity ensures the transaction is all or nothing, meaning no half-finished money transfers. Consistency guarantees we don't break data rules, like creating money out of thin air. Durability means once a transaction is committed, it survives a server crash. But when we're talking about race conditions, isolation is really our hero here. Isolation is specifically designed to ensure that concurrent activities, like our two threads from earlier, absolutely cannot stomp all over each other's calculations and destroy the data.
To enforce this isolation, a database carefully manages the lifecycle of every single transaction. If a conflict is detected, let's say thread B tries to write to a record that thread A is currently updating, the database immediately steps in. It changes the transaction state from active to failed. It aborts the process, effectively rolling back any intermediate changes to protect the system's integrity, which ensures the shared state remains uncorrupted.
Section 3. Real-world catastrophes. Let's see what happens to life-critical systems. What happens when these isolated digital errors spill over into the physical world? Well, race conditions in life-critical systems can be absolutely devastating. A tragic example of this is the Therac 25 radiation therapy machine. The system had a shared global counter between the operator interface and the treatment delivery system. If an operator typed a very specific sequence of keystrokes within a precise, tiny timing window, a race condition caused the counter to overflow. This literally removed the software's safety locks, delivering massive, fatal radiation overdoses to patients. And it took months of investigation to even reproduce because the exact timing was just so rare.
We also have to look at the 2003 North American blackout,
which left an estimated 50 million people without power. An energy management system utilized by First Energy Corporation had a race condition buried deep within its alarm subsystem. When 3 sagging power lines tripped simultaneously, the resulting race condition actively prevented alerts from reaching the monitoring technicians. Because they were totally blind to the cascading failures, the technicians couldn't intervene in time, which led to a historic blackout.
Even our most advanced space exploration technology isn't immune to this. Shortly after landing, the Mars rover Spirit suffered a near loss due to a race condition in its file system. It was a classic time of check to time of use flaw. The system checked for available resources, but right before it could act, deleted file entries caused the system to suddenly consume all available memory space. The rover became critically destabilized simply because unrelated programs tripped over each other's resource management.
Section 4. Synchronization and prevention. How do we stop these errors?
Now that we've seen the devastation these timing bugs can cause, how do engineers actually restore order? Well, while executing transactions serially, just one after the other, is the safest method, it's obviously terrible for efficiency. So to achieve speed without sacrificing safety, databases use a clever concept called conflict serializability. The database basically acts as a traffic controller, swapping the order of non-conflicting operations behind the scenes. It creates a schedule that processes concurrent transactions so perfectly that the final result is exactly equivalent to them running safely in a single serial line.
Beyond the database level, software engineers have quite an arsenal of prevention tools. A core concept here is mutual exclusion, which is very often implemented through mutex locks. Think of a mutex lock like a bouncer at an exclusive club. The club is the critical section of your code where your shared data lives. The bouncer ensures only one thread can ever enter that room at a time. All other threads have to wait at the door until the first thread finishes its business and unlocks it. We also use atomic operations. These are actions mathematically guaranteed to complete fully without ever being interrupted by another thread.
Section 5. The power of restraint. Let's talk about visualizing this complexity.
Explaining race conditions requires visualizing some highly complex data. Think about a traditional 3D animation approach. It often bombards you with fast pacing, complex sweeping camera angles, and hyper-detailed backgrounds. It's chaotic, honestly, very much like an unmanaged concurrent server. But contrast that with a deliberate, minimalist aesthetic. Slow, careful motion, minimal backgrounds. By removing that visual noise, we aren't doing less work. We're actually using restraint to help your brain process complex technical concepts faster and much more clearly.
And this brilliantly illustrates a real connection. Just as good software design removes the chaos of data races, good visual design removes visual clutter. Using clean backgrounds, soft lighting, and intentional negative space gives the data room to breathe, which drastically reduces your cognitive load. Every frame has a defined purpose, moving with smooth, physics-based precision. You can think of it as the visual equivalent of a perfectly executed, mutually exclusive atomic operation. Ultimately, whether we are talking about millions of web requests or rendering stunning 3D graphics, concurrency is incredibly powerful. The ability to do many things at once is literally what makes modern computing, cloud infrastructure, and real-time systems even possible. It gives us unprecedented speed.
But without strict synchronization, it becomes intensely dangerous. The space between overlapping threads is exactly where data corrupts, accounts strain, and life-critical systems fail.
So, as we wrap up this explainer, I really want you to take a hard look at the architecture of the systems you rely on, or the systems you build. Are your critical sections truly structurally secure? Or is your database just one unmanaged millisecond away from a catastrophic data race? Think about it.